So the magnetic field created by a moving charge. We have a nice little equation. So again, the symbol we use for magnetic field is a capital B. Magnetic field is a vector. It has a direction associated with it. The equation looks like this. Mu naught is a constant. So with electricity, remember we saw epsilon naught a lot? Mu naught is the constant we see a lot with magnetism. Its value is 4 pi times 10 to the negative 7 Tesla meters per amp, I believe is the units. So it's a small number. Q in here is the charge of the moving charge that's creating the magnetic field. So whether it's positive or negative is going to be important. V is the velocity of our moving charge. Like we said, magnetism is due to moving charges. If our charge is not moving, if V is 0, then it's not producing a magnetic field. V is 0. Okay. So the charge must be moving.
That's a cross, right?
It is a cross product, yes. So yeah, that's not a variable x. It's across the specific function. R hat is the unit vector describing the direction between the charge out to where you want to know the magnetic field. And R in the denominator is the distance to the point you're interested in. So for example, let's say we have a little proton and it's moving towards the top of the board. So it has some velocity v. Number 1, because of the cross product, remember the cross product multiplies perpendicular components, and the result is always perpendicular to either of those two vectors. V is the direction the charge is moving in. R hat always points from the charge to the point you're interested in. If we were interested in finding the magnetic field at a point right here, R hat would point straight up towards that little dot. V and R hat would be parallel to each other. Well, cross product only multiplies perpendicular components. If V and R hat are parallel, when you cross them, you get 0. What that means is this charge, as it moves, it does not create an a magnetic field anywhere along that line. Okay? Its magnetic field is not anywhere along that line. It doesn't create anything there. It does create a magnetic field off the axis. So for example, over here, that charge will be creating a magnetic field. The velocity is still towards the top of the board. That's the direction our charge is moving in. R is the distance from this charge out to the point we're interested in. So that's R. R hat is the unit vector that lies along that line and points in that direction. Points out towards the point we're interested in. So that's R hat. In this case, the velocity and R hat are perpendicular. So the value of the magnetic field out here is going to be mu naught Q. When we take V across R hat, they are perpendicular, so we're going to need the magnitude of V. The magnitude of R hat is just 1. Any unit vector has a length of 1. So that will be the magnitude of the magnetic field at that point. But magnetic field is a vector. We need to write it as a vector. So V is in the j hat direction. Crossed R hat is in the x direction. J crossed with I is negative k. Now there's a nifty little right-hand rule. that works for cross products. If you don't have the J cross I is negative K and J cross K is I and so forth, if you don't have those memorized or have a way to remember them, the right-hand rule works quite nicely. Number one, you gotta use your right hand, hence the name, right-hand rule. Those of us who are right-handed are the ones that always do it backwards because you're holding your pen in your right hand. You don't want to set it down, so you try to use your left hand. And the left hand always gives you the opposite answer. So right hand, index finger. This right hand rule works for any cross product equation at all. That's the nice thing. So the first vector in the cross product you point your index finger in that direction. So your pointer finger. So V is that way. The second vector, you need to keep your finger pointed that way and turn your wrist around until the second vector points out of your palm. So I have my index finger pointing up because that's the direction of the velocity. In our picture here, our hat's to the right. Well, I need to keep my index finger up, so I need to turn my wrist until out of my palm is to the right. And my thumb is the result. My thumb is pointing into the board, which in a traditional X, Y, Z axis, Z would be out of the positive Z would be out of the board, negative Z is into the board. So this magnetic field vector is in the negative k hat direction. If we're doing X being horizontal, Y being vertical, then Z's in and out of the board. If you remember or have a way to remember the cross product rules, then go ahead and use those, that's fine. To represent in and out of the board, since three-dimensional is kind of difficult to draw, vectors, we've been drawing vectors as an arrow. If you imagine an actual arrow, so you're out with your bow and arrow, if something was coming out towards you, you would see the tip of the arrow coming at you. So the symbol we use to represent out of the board is a little dot with a circle around it. So dot meaning the tip of the arrow coming at you. If you were the one shooting the arrow and it was moving away from you, what you would see is the crosshairs, those little feathers at the back of the arrow. So to represent into the board or into your paper, we use a little X with a circle around it. So to draw the direction of this magnetic field right here, since it's into the board, we would say a little X with a circle around it to represent the direction of that magnetic field.
So there's rings around.
Exactly. So if we wanted to look at the same distance but on this side, our hat would now be pointing to the left, so J cross negative I hat, or right hand rule, index finger in the direction of V, this guy out of my palm, my thumb points out of the board, this magnetic field here would be coming out of the board. It would have the same magnitude. It would be coming out of the board. Out here, a point out here, the magnetic field would be pointing to your right. So the magnetic field is actually making circles around that charge. If that charge was headed towards you, you would see counterclockwise circles of magnetic. Well, you can't really see the magnetic field. But if you could see the magnetic field, it would be making counterclockwise circles around that charge as it moved towards you. Okay. We can represent that pictorially. Positive charge with the velocity coming towards you. So the little dot to represent the velocity. So if it's coming towards you. The magnetic field. It's an ugly circle, sorry. Make circles around the charge. What if it was a negative charge coming towards you? Negative charge would have a negative sign on Q. So whatever you got for V cross R hat times a negative sign just changes the direction. So positive charge is coming towards you, it makes counterclockwise circles. If it's a negative charge coming towards you, it makes clockwise circles. So a moving charge creates a magnetic field. The magnetic field makes circles around it. They're complete loops. They don't start and stop. They're complete circles. Okay? So we could have sets of magnetic fields. A whole bunch of different rings to represent the magnetic field at different distances away. How strong the magnetic field is depends on not only how much charge you have and how fast it's going, but how far away you are from the charge. So the field gets weaker and weaker the further away you are from any one given charge.
Does it get to zero eventually?
Yeah, you'd have to define what's small enough to be zero for you, but yes, eventually this term is going to get very, very small. This equation, please keep in mind, this equation describes the magnetic field a moving charge creates. Okay? A moving charge cannot exert a force on itself. So if our charge is moving in a region where there's an additional magnetic field due to something else, say another moving charge, then they can interact. But if you have solely one little charge creating a magnetic field, it's not going to exert a force on itself. Okay? Its magnetic field, it can be found using that equation. That magnetic field can interact with other magnetic fields. We're going to talk about the force on a charge that's moving in a field. But we have to use a different equation.